All right. This next section, 6.3 in the textbook, is on step functions. Step functions. So we have already seen the general procedure involved in solving an initial value problem using the Laplace transform. However, it turns out that some of the most useful applications of the Laplace transform method occur in the solution of linear differential equations that are non-homogeneous, and the non-homogeneous term is discontinuous. So it has discontinuities. And equations of this type arise actually often in the analysis of the flow of current in electric circuits, and even also in uh, the analysis of vibrations of mechanical systems. So in order to deal with discontinuities, especially jump discontinuities, which are the ones that are most frequently encountered, it is helpful then to introduce a function that is called the unit step function, or the Heaviside function. Heaviside is the last name of a guy called Oliver Heaviside, and he was supposedly a self-taught mathematician, physicist, and electrical engineer. And he introduced this function to uh, to deal with DPQs, and he also uh, used complex numbers in the mathematical analysis of electric circuits. So he's known for that. He did more stuff than that, but I'm just mentioning those two. Okay, so here's the Heaviside function. Suppose that you have a constant that is bigger than or equal than 0. So the constant has to be 0 or bigger. Then the corresponding unit step function or Heaviside function at t equals c, so the corresponding unit step function or Heaviside function at t equals c, and we use the notation UC, so unit step function, so U for unit step function, and the C becomes a subscript. So UC is defined as follows. UC evaluated at t is going to be 0 if t is between 0 and c, but it is not c, so it is strictly less than c. And then starting at c and onwards, it is 1. So it's a function that is 0, 1. And if you graph it, well, the graph is going to look like this. Between 0 and c, but not including c, so like there's a hole there. Then the value is 0. And then starting at c, and that's included, you see it's filled in. Starting at c, the function is constant 1. So the function takes only two values, 0 and 1. And that's supposed to represent a signal that switches on at a specified time. So it's like you turn the switch on at t equals c. So before you turn the switch on, the function is 0. 0. Like there's no light or electricity flowing in, 0. And then once you switch it on and send the signal, then it's fully lit, or electricity is flowing in at a steady rate. So it's like you turn a switch right at C. At time equals C, the switch is on. So from that point onward, the value is 1. Before t equals C, the switch is off, so the value is 0. So that would be the graph of UC of t. 0 and 1. Now, it is also useful to consider sometimes the function u1 minus uc. 1 minus uc. So 1 minus uc, well, if in this part is going to be 1 minus 0. 1 minus 0 is 1. So that means in this part is going to be 1. And then after c, 1 minus 1 is 0. So after c, this is going to be 0. So the function 1 minus uc has this graph. Is 1 between 0 and c, but not including c. And then it is 0 starting at c. So it's like the opposite. This one starts on and then switches off at t equals c. Okay, so for some practice, we're dealing with these Heaviside functions. We're going to sketch a couple of graphs to see how this works. And you have to be careful because this, could confuse you really quickly, throw you off because of the on and off and whatnot. So here's the graph I want to sketch. Let me zoom in. We're going to sketch the graph of g of t equals u sub 2 with a Heaviside function at 2 evaluated at t plus 3 times the Heaviside function at t equals 3 and minus 6 u4. So u2 plus 3u3 minus 6u4. All right. So you see there's 3 different indices happening at 2, 3, and 4. So that means that each of these moments in time, you can think of them as moments in time, at t equals 2 seconds or 2 minutes or whatever the units are, at t equals 2 seconds, let's say, the switch is turned on. Another second later, then it's turned off. I mean, this one is turned on again, and this one is turned on at 4. So there's 3 moments in time where some turning off or on is happening. So those are the key moments then. That means the graph of this is going to have steps, and there's going to be some changes happening at 2, at 3, and at 4. So that means g of t then is going to be a piecewise defined function where the key moments are between 0 and 2. Then something happens at the next time will be 3, so between 2 and 3. And then between 3 and 4. And lastly, after 4. So actually then the graph is broken up into 4 pieces. There's 3 moments. There's 3 moments where something is happening. So if you have a line starting at 0, there's 3 moments where something is happening. You have 2, 3, and 4. So that breaks up the domain into 4 pieces, between 0 and 2, between 2 and 3, between 3 and 4, and between 4 and infinity. Right? So you should have 4 pieces. Okay, it's broken up like that. Okay, now let's figure out what happens between 0 and 2. Alright. If you plug in a number between 0 and 2, and there's no changes between 0 and 2, the only changes that are happening happen at 2, 3, and 4. So if you plug in a number between 0 and 2, that should be a constant value for all the numbers between 0 and 2. So let's pick any random number between 0 and 2 that is easy to deal with, such as 1, and let's plug it in and see what we get. So we have plugging in 1, so we're going to figure out what g of 1 is. u2 of 1 plus 3 u3 of 1 minus 6 u4 of 1. Okay, 1 is happening before 2. So before, remember that u2 switches on and becomes 1 right at 2. So before 2, it is off. So that means the value is 0. The value is 0 before that C. In this case, the C is 2. So if I plug in 1 in this one, I'm supposed to get 0 because it's turned off before 2. So at 1, it's off. So the value is 0. When you plug in 1, again, that happens before this function is turned on. So it happens before 3. So that is also 0. This function is off before 3. So this is 3 times this 3 times, and then this is 0. And then if you plug in 1 in U4, again, that's still off. This one turns on at 4. So it becomes 1 at 4, but before that is 0. So that is 0. And then that is 0 plus 0 minus 0, which is 0. So that means between 0 and 2, g of t is 0. Okay, now let's figure out what is the value at a number between 2 and 3. Let's pick, I don't know, 2.5. You could have also picked t equals 2, but just to make it even clearer, still, let's pick a number that is right in the middle, 2.5. So now this means u2, 2.5, so I'm just going to copy this, plus 3, u3, 2.5, minus 6, u4, 2.5. Okay, so let's see. If I plug in 2.5 in U2, well, 2.5 comes after the switch has been turned on, so that means the value is 1. So U2 of 2.5 is 1, because 2.5 happens after the switch has been turned on, so the value is 1. Now 2.5 evaluated on U3, that one is 0 because 2.5 happens before the switch is turned on. So this is 0 right here. It happens before. So that is 0. And similarly for this one, 2.5 happens before 4. So before 4, U sub 4 is 0. So this one is going to be 0. So 1 plus 0 minus 0 is 1. So the value there is 1. Okay? Now let's plug in a number between 3 and 4. So let's say 3.5. U2 of 3.5 plus 3 U3 of 3.5 minus 6 U4 of 3.5. Okay, U2 3.5 happens after the switch has been turned on for this function, so that should be 1. 3.5 happens after 3, after this one has been turned on, so the value is 1. And then 3.5 happens before 4, so that means this one is 0. Now 1 plus 3 minus 0, that is 4. So that means the value between 3 and 4 is 4. Okay, and lastly, if I plug in a number bigger than 4, let's say 5, u2 of 5 plus 3, u3 of 5 minus 6, u4 of 5. If I plug in 5, that's happened after 2, so this function is switched on, so the value is 1. Similarly, 5 is after 3, so the value is 1. And 5 happens after 4, so the value is 1. We have 1 plus 3, which is 4, minus 6. 4 minus 6 is negative 2. So that one then is negative 2. Okay, so that is G. Now we can sketch this. Okay, so let's see. If I go, let's go by ones. So I'm gonna zoom this. I'm gonna zoom in. Okay, so let's sketch this now. So between 0 and 2, the value is 0, but not including 2. So that means in this piece, you get 0. And there's a hole at 2. Now between 2 and 3, the value is 1, but you include that one, and not the other one. Oh, that should have been between 2 and 3. You see, this is too tiny. This is too small. Probably should have gone. Let's start over and go. Let's go by 2s because this is so small. Let's draw the scale where we go by 2. Okay. So that means this is 1, 2, 3, 4. 1, 2, 3, 4. Okay. All right. Let's say start over again. Between 0 and 2, the value is 0. So you have a 0, and then you have this. Okay. This one is included, by the way, at 0 to 0. Okay. Then between 2 and 3, the value is 1. So between 2 and 3, the value is 1. This one is included, but not that one. And then between 3 and 4, the value is 4. Between 3 and 4, the value is 4. This one is included. This one is not. And after 4, the value is negative 2. So this is negative 1, negative 2. This one is included, and that goes on forever to the right. Okay, that's the graph of GFT. Okay, now we're going to do another example of the same type. Okay, this one is just slightly more complicated. Not too terrible, but just slightly different. Um, and here's the difference. If you look at the coefficients of the u's here, the coefficient is 1, the coefficient is 3, the coefficient is 6, negative 6. So these coefficients are all constants. So that's why we got here, everything was a constant. But in this one, the coefficients are not constants. So that means by just picking one number in between each of the parts that G is going to have, instead of picking one number, that's not going to exactly work because in each of the pieces, the numbers are changing. This is not constant. So that's the difference. So let's see how we figure this one out. Okay, the breakup happens again on the indices that you see. So there is something switching on at 2, and there's another change here at 3. Okay, so now there's a change at 2 and 3, at 2 and at 3. So that means the domain is going to be split up into 3 pieces between 0 and 2, 2 and 3, and 3 to infinity. And remember, for the Heaviside function, you include the left. Okay, so anyway, now let's see. So g of t is going to be broken up into 3 pieces between 0 and 2, between 2 and 3, right? Remember, that's where the breakups between 0 and 2, 2 and 3, and 3 and 2, and 3 to infinity. And then 3 to infinity. Alright, so let's see what the values are. Now, we pick a number between 0 and 2. We pick a number between 0 and 2. And between 0 and 2, so the switches are going to be either on or off. If I were to pick a number, let's say like 1, then when I plug in 1 in U2, I would get 0. But now we have to do this in the abstract again because this is not a constant coefficient, so we have to think about it a little bit more in the abstract. So if I choose a number between 0 and 2 and I plug it in g of t, in g, you will get, okay, this is what you get, but now we're going to simplify it. If t is between 0 and 2, then this actually right here is 0. Because if t is, oh, that should have been a 2, my bad. Because if t is smaller than 2, then this is off. This function turns on at 2. So if I'm plugging in a number that is smaller than 2, this whole piece is 0. That whole piece is 0. So this is going to be t minus 3 times 0 minus t minus 2 times, now if I plug in 2, I mean a number smaller than 2, this is also 0. That one is also 0. So this is going to be 0. So you get 0 minus 0, which is 0. So between 0 and 2, this is 0. Okay, now let's plug in a number between 2 and 3. Okay, if I'm plugging in a number between 2 and 3, such as 2.5, well, if t is bigger than or equal than 2, then this is 1 because I'm plugging in a number that is bigger than 2. It happens after the switch has been turned on, so this is 1. So then this would be t minus 3 times 1. Only this part, right? This, I cannot say what this is because it depends on what I'm plugging in for t. So this is, you cannot simplify this one, you just have to leave it like that because t is variable. However, regardless of whether t is variable or not, if I'm plugging in a number between 2 and 3, this is going to be 1, because I'm plugging in a number that is bigger than 2. And then this right here would be 0, because I'm plugging in a number smaller than 3. Smaller than 3, that means I'm plugging in a number that happens before the function has been turned, the switch has been turned on. So that is 0. And simplifying, this is just t minus 3 minus 0. So this is just t minus 3. Minus 3. Okay? And lastly, if we plug in a number bigger than 3, if you plug in a number bigger than or equal than 3, then this one, because I'm plugging in a number bigger than 3, this is bigger than 2. So this is 1. So this is going to be t minus 3 times 1 minus t minus 2. And then this is times 1 as well, because I'm plugging in a number that happens after it has been turned on. Plugging in a number bigger than 3, so this is 1. So then simplifying, this is t minus 3 minus parentheses t minus 2, which is t minus 3 minus t plus 2, so this is negative 1. So this is negative 1. And now we have a full description in its various parts of the Laplace transform. I mean, sorry, of the function g. Now that I mentioned the Laplace transform by accident, it is going to be a lot easier to find the Laplace transform of something when you have a single formula than something like this. So we eventually do a few examples where you have a piecewise defined function and you want to find the Laplace transform of that. Well, that's not as simple unless you have it like this. Okay, so now let's sketch the graph of this. So between, I'm going to go by twos, let me see, by twos again, yeah. So this is going to be 1, 2, 3, 4, 5. 1, 2, 3. 4. Okay, between 0 and 2, the value is 0. So between 0 and 2, the value is 0. So a hole there, and you have that. Between 0 and 2, the value is 0. Okay. Between 2 and 3, you have t minus 3. Well, that's a line. That's the equation of a line. So that means we're going to have, we're going to have a piece of the line between the segment of the line that is between 2 and 3. But if we didn't have restrictions, t minus 3, that would be a line. So what we're going to do is draw this line by drawing the beginning and the end, plotting the beginning and the end. So when the beginning of this line between 2 and 3 would be right at when t equals 2. When you plug in t equals 2 here, you get 2 minus 3, which is negative 1. So right at 2, you get negative 1 right there. Okay, now, if I were to include the end of this, which I'm not going to include because it's not allowed, but if I were to include it, it would end right at 3. And when you plug in 3, 3 minus 3 is 0. So that means it would end right here. And we connect those. That's that piece. And lastly, for t bigger than 3, or bigger than or equal to 3, you get negative 1. So now negative 1 is that, and that goes like that. And that is the graph of g. Okay. All right. One more thing on this page. For a given function, suppose that you have a function, we sometimes want to consider a translation of the function. A translation by a number, meaning you take the graph and move it all the way to the right by c units, uh, by a distance of c in the positive direction. So if you remember from college algebra, to move something to the right, you subtract a number. So to move it by c units to the right, you subtract a number. So you subtract c. So the function that we want to consider, that is a translation of f by a distance in the positive direction, is this new function defined here. Starting with f, this function g, defined in terms of f, is a translation of f by a distance c to the by a distance c in the positive direction. So now this one is going to start at 0 and end at c, and after c it has this value. Starting at c has this value. You can simplify this formula right here by just writing it like this. So it is g of t equals the unit step function at c times f of t minus c. And you can see that it's the same thing because you start out with this. Let me write that here. You start out with that, which is I just copied that. You can see that you can factor out the f of t minus c from both. Well, from 0, which is going to leave you with 0. And then factor in the f of t minus c from the bottom is going to leave you with 1. Okay, now this right here, that is the Heaviside function at c. So you see that this is then equal to f of t minus c uc of t, which is precisely this right here. Okay, same thing. Okay, so now with that we're going to mention the next theorem. So this theorem allows you to figure out the Laplace transform of functions like this, where you have translation of a function, where you have a translation of a function by a distance of c in the positive t direction. Okay, so here's what the theorem says. Figuring out the Laplace transform of this is not hard. If you have a function like that, which you can write like this, or that, same thing, then the Laplace transform of this thing, the Laplace transform of that thing equals e to the minus cs times the Laplace transform of f. And that's that. I mean, and figuring out this formula is not hard. You can start with the very definition of the Laplace transform and figure it out. It's really not difficult. You can try it on your own. I'm not going to do it, but this formula right here is not nothing mysterious. You can just use the very definition of the Laplace transform to come up with that formula. Do the integral, the integral from 0 to infinity, blah blah blah. Okay, so the Laplace transform of that, the translation of f by c to the right, or uc evaluated t of f t minus c, is given by this. So e to the minus cs Laplace transform of f. Note that the u, once you take the Laplace transform of that, the u function disappears, is no longer anywhere to be seen, and you end up with e to the minus cs times the Laplace transform of f. Another thing that you have to notice is that this c, which is a subscript, and the minus c, it has to be the same c. So if those two numbers are not matching, you cannot use this. In other words, if I was trying to figure out the Laplace transform of something like this, u2 of f of t minus 3, then I'm stuck because I cannot use the formula. These numbers have to match exactly. So either this one is a 3 or that one is a 2, but they have to be the same. If this is what I have, I cannot use this formula. And we're going to encounter actually stuff like this, and we have to just make it work by making some tricks, some modifications. We have to force them to be the same. You have to force this one to be a 2, basically. Alright, so that's the formula. E to the minus cs times the Laplace transform of f. Conversely, if you're going in the opposite direction, then the Laplace inverse of this is going to be uc of t times f, little f being the Laplace inverse of capital F, at t minus c. Remember that capital F is a Laplace transform of little f, or little f is the Laplace inverse of capital F. Okay? Alright. Now let's do a couple of examples regarding this theorem. Alright, first one says find the Laplace transform of f of t equals 0 for t between 0 and 2, and then t minus 2 squared for t bigger than or equal than 2. Okay. You could either memorize that formula, that you could write it like this, or do what I do, which is basically go through this process all the time, because I don't like memorizing that. I mean, it's not like a big formula or anything, so it's not hard, but I find this easier to remember in general, to be honest. So that's the way I'm going to do it. So this is going to be f of t equals, so I'm going to factor out the t minus 2 squared from both. So this is f of t equals t minus 2 squared, and then you factor it from both of them, and you end up with 0 and 1. Okay, and now this piece right here is precisely the Heaviside function at 2. So this is actually, this part is the Heaviside function at 2. Okay, and that is rewriting that into a single formula. And now you can take the Laplace transform of this. The Laplace transform of f of t equals the Laplace transform. Well, I'm taking L on both sides, so this is equal to Laplace transform of t minus t squared u2 of t. And according to this formula, which I can use because note that the number, the translation, and the little index match. They match perfectly, so I can use this. This is going to be e to the minus cs, the c being 2. So here the c is 2 in the formula. So this is e to the minus 2. Sorry. Yes, that's right. C is 2. To the minus 2 s Laplace transform of what? Of this. Okay, the notation might be a little bit confusing, but it would be the Laplace transform of this one. You see, it is this whatever I have next to the u without the translation. So it is this that I have next to the u without the translation. So it's going to be Laplace transform of. Okay, so take a look at that carefully. So this is the Laplace transform of uct times f of t minus c. As long as the numbers match, this is e to the minus cs Laplace transform of f, where f is what is next to the u without the translation. So here it would be Laplace transform of this, the thing that is next to the u without the translation, without the minus 2 part. So it will be t squared. Okay, times the Laplace transform of t squared. And now we have to look up what is the Laplace transform of t squared. Okay, and that we just look it up in the table of Laplace transforms. So the Laplace transform of t squared, well, this one, when n equals 2, the Laplace transform of t to the n, so this row, when n equals 2 will be this, will be 2 factorial over s to the 2 plus 1. So I'm going to use then number 3 in the table of Laplace transforms and say that this is equal to e to the minus 2s times 2 factorial from the table over s to the 2 plus 1. Okay, so this is simplifying e to the minus 2s. 2 factorial is 2, and this is s cubed. And that is the answer. You can put it all as a single fraction if you want to, but that is it. That is a Laplace transform over the given function. Okay, let's do another one here. Find the Laplace transform of that. Okay. We're going to, if you notice that, if you look at that, that is, I need to write this like a translation of something. And this is a parabola that has been transformed. So you start with a basic one and then you move it around. And that's basically it. This is a modification of a parabola, the second part. So it is going to be a translation of the parabola, and we have to write it as such. For that, we're going to complete the square. So let's do that. So let's complete the square. This is t squared minus 6t. And then complete the square right now. So completing the square, what do you add to complete the square of this? Remember, you divide the coefficient by 2, you get -3, and then you square it, so 9. Okay, so that makes a complete square, but that's not what I originally had. I had plus 10, so to bring it back to what it was supposed to be, I need to add a 1, and now it will be plus 10, and now that will be perfect, because then that means that I have not changed anything. Okay, so this is that between 0 and 3, and that for t bigger than or equal to 3. Okay, so now writing this, after completing the square, this is t minus 3 squared. This part is t minus 3 squared plus 1. Okay, there we have it. And now, you see, looking back at the formula, let me see where I put it. Oh, yeah, the formula right here. If we use the formula this time, which sometimes it is convenient. So you have 0, which I have that, and then a translation of something by a number. Okay, so this is something translated by C. This is something translated by C, where C is the same as that number, C is 3. So what is it? This is, bottom right here, is a translation of the function t squared plus 1. T squared plus 1, and it's translated by 3. So this is t minus 3 equals 3, t minus 3 squared plus 1, right? If I start out with this function, t squared plus 1, so basically I'm ignoring the translation. If you ignore the translation, that's what you have. You have t squared plus 1. The minus 3 part is the translation. So this original function, if you were to plug in t minus 3, you would indeed get this. So this is then equal to this. You see? Okay. And now, what does that give me? Well, now I can say that this is equal to g of t minus 3 times u3. Right? You could pull that out, and then you would have 0, 1, etc. So that's what you get when you write it in terms of u. So g of t minus 3 times u of 3. And now this is ready to go. Now we can find the Laplace transform of this. So now, the Laplace transform of f of t, find the Laplace transform of this. This is the Laplace transform, put in L on both sides. This is the Laplace transform of g of t minus 3 times u3 of t. Okay, now we can use the formula. Formula tells me if I want to find the Laplace transform of u of a Heaviside function times some translation, then I get e to the negative cs times the Laplace transform of the function next to the u without the translation. So this is going to be then e to the negative 3s. Note that 3's match. If these didn't match, I couldn't do anything. E to the minus 3s times the Laplace transform of the g without the translation of that. Now, g of t is t squared plus 1, t squared plus 1. And now the Laplace transform is linear, so you can say this is actually the Laplace transform of t squared plus the Laplace transform of 1. And now you look these up in your table. Where's my table again? Here it is. The Laplace transform of t squared, this one is that. So 2 factorial over s to the 2 plus 1. So using number 3 right here, I'm probably going to use another one. Okay, yeah, this is 2 factorial over s to the 2 plus 1. You can just write 3 right away, so you don't have to write the whole thing. And then Laplace transform of 1, the Laplace transform of 1 is 1 over s. So I'm using also number 1, 3 and 1. So this is 1 over s. And simplifying just a little bit, this is e to the minus 3s, e to the minus 3s times 2 over s cubed plus 1 over s. Okay, that is the answer.